Hello everyone. In this video we're going to be talking about linear programming, what the canonical linear programming model is. First of all, a linear programming model is an optimization problem in which we want to maximize or minimize a given objective function subject to some constraints, in which all my functions are linear, right? And the type of solution approaches that exist in the literature, well, there are many, right? But we're gonna take a look at the simplex method. We'll see how to solve it from both the geometric and an algebraic perspective. These solution approaches, in particular the simplex methods, are the ones that come implemented into the solvers we're going to be seeing in the labs. But I would like you to have a brief overview on what they consist of, what they do, where the particularities. Other type of solution approaches that you might check, dual simplex. We have the interior point method, upper bound method, and parametric linear programming. But in any case, we stick to the simplex one. Well, let's start by stating the canonical. This is the canonical linear programming model, and this is going to be important, right? We will see why. The canonical linear programming model is stated as follows. We want to maximize objective function set made of c1 times x1, c2 times x2 plus cn times xn, and this is the objective function subject to a set of constraints, and these read as follows: a11 times x1 plus a12 times x2 plus a1n times xn lower or equal than a given parameter v1, and this is restriction number 1. We have the same a21 x1, a22 x2 plus a2n xn lower or equal than v2. This is the restriction number 2, and we move down and we have am, right, because we have m restrictions, m1 x1, m2 x2 plus amn xn lower or equal than bm, right? In this model, x sub I belongs to the real positive, or in other words, x1 is greater or equal than 0, xn greater or equal than 0. And these are the decision variables, right? I need to find the best combination, or the combination that meets the constraints and at the same time maximizes the objective function. Aij bj, right? I1 to m, j going from 1 to n are the parameters of my model, right? Which something that is known. And this is the canonical or a canonical linear programming model. This is important because here we are dealing with computers, and computers are not smart enough to identify whether this is the way you've formulated the problem is canonical or not. So in what has to do with the algebraic procedure and all the things we need to feed to the computers, we are always going to transform our optimization problem to this canonical one and then feed the solvers, right? So it's true that we can have problems in which we minimize set, and you might say in a linear problem is very easy to transform a minimization to a maximization by manipulating the objective function. It's true, but we need to do it, okay? We might have equality constraints, right, in which a11, x1, a1m, xn is equal to b1 equality. This will work, but again, we need to transform it into the canonical one, or something that is greater or equal than a given parameter, right? Or our decision variables that are real negative. We will see how to transform these non-canonical ways of formulating a linear programming problem into the canonical one, right? If we go back to our model, you see that this can be easily transformed into the matricial format. So we can have the same formulation as follows. We want to maximize set, which is a scalar, equal to C transpose, right, times X, subject to A, this is a matrix, times X lower or equal than V, and this is a column vector, in which the vector of decision variables X is greater or equal than 0, or it belongs to the real positives, right? And we will have that C is the column vector C1 to Cn. We will have that X is the column vector x1 to xn. Sorry, with the notation. We'll see that V is again the column vector b1 to bm, so belongs to Rm. And what else? And my matrix A, which belongs to Nm, reals Nm, is equal to A11, A1n, AM1, AMN. Right. When it comes to incorporating a non-canonical format, we can include a column vector of equality constraints, or something like B equality, right? Then you'll have B1 equality, Bm equality, and a vector of a matrix, sorry, of A equalities in the same manner, okay? But in principle, we always stick, this is non-canonical, right? We will have something like A equality times X equal B equality as an additional equation, but again, this is non-canonical. So you can see how to formulate a canonical linear programming model, both using algebraic equations and using matrices, and we will see this in the example that will come afterwards. Thanks very much.